Hello everyone, this is the second lesson of topic 5. It's the second lesson and the last lesson, so when we finish it, you have all the contents that you need for the first midterm exam. Okay? So after watching the video, let me know you have doubts, so that you can do the exercises of the list of exercises posted in the virtual campus. So, if you remember, we saw the definition and properties for the minimal synthesis. That is, how to simplify a function using Karnaugh map as a graphical tool with some concepts. If you remember, we saw that covering a function is to include all the ones of the function in the Karnaugh map into implicants. Okay? If we include all the ones of the Karnaugh map into implicants, we have covered the function. So we can have a Karnaugh map here, for example, and we have, this is a 4-variable Karnaugh map. Well, it doesn't matter. So the complete sum is the sum of all the prime implicants of the functions. Remember that an implicant is the product term associated with each allowed group of ones. The allowed group of ones are those that form a square or a rectangle in the Karnaugh map, and the number of cells, the number of ones inside them, are a power of 2. So we can link this rectangle or square with a product term. Remember that we used the variable that don't change across all the allowed group of 1 to form the product term. The variable is going to be non-negated if it's 1, and complemented or negated if it's 0. I'm using negated and complemented as synonyms. So complemented is just negated a variable, okay? Just in case you didn't realize. The irredundant sum is a sum so that if we remove one product terms, one implicant of the function, we are leaving ones out that are not covered. For example, if we have these ones here, we can form this prime implicant, for example. So if we don't include this product term, this one is going to be out of is going to be uncovered. So the redundant sum is going to include all the prime implicants, so that if we remove one of them, we are going to leave ones uncovered. An essential prime implicant is a prime implicant that covers distinguished shell. This one here is a distinguished shell because it's only covered by this prime implicant. So this prime implicant is essential because if we don't use it, we leave this one uncovered. Remember that a prime implicant is the largest group that we can form to cover the ones of the function. For example, this should be an implicant of the function, but it's not a prime implicant because we have that these ones can be covered by a larger one. So the larger one, the 4-1 size, is the prime implicant here, and this implicant is an implicant but not a prime implicant because we have another containing it that is larger. The minimal sum is going to be the redundant sum with the fewest prime implicants. So if we have a sum, a redundant sum, that is plus B plus C plus D, and another irredundant sum that is A plus B plus C, being A, B, C, D product terms, this is going to be the minimal sum because the number of prime implicants involved is smaller. And the strictly minimal sum, if we have two irredundant sums that has the same number of implicants, we are going to see how these product terms are formed, and we are going to choose the minimal sum whose implicant has fewer literals. Remember that the literals can be a constant of a variable. In this case, they are variables, okay? And here we have this, the property for minimal design. We can have the strictly minimal sum in a two-level and or realization, okay? That means that when we translate the expression, the algebraic expression of the function, into a circuit formed by logic gate, we are going to have always a two-level and or. I'm going to give you an example of this. Imagine that we have this minimal sum. Imagine that this is the minimal sum of a function, okay? I haven't checked it, maybe it's not. Maybe I'm making a mistake, it's just a quick example. So, if we look at this, we are going to have here an OR level. And inside the product term, we have AND operations, because they are products. So, if we represent in a logic circuit this function, we are going to have an OR in the output whose input are going to be two AND gate in this way. Here we have xy, and here s negated y, and here the sum of the input. So you can see that we have two levels of gate. Remember that we have different levels when we have a gate connector ones after the others. So the first level is formed by AND gates, and the second level is formed by OR gates. Always that we use the minimal sum or the strictly minimal sum, we are going to have this kind of circuit. It's going to be larger or smaller depending on the number of literals and implicants, but we are going to have always two levels. So if you have an exercise in which they tell you that you have to obtain an implementation with a logic circuit using a two levels and OR, they are telling you that you have to calculate the minimal sum. We have the dual thing for the minimal product. Imagine that we have this, the minimal product. We have this example. It's a different function that is a product of some terms. In this case, we have that the minimal product is like this. You can see that we are going to have at the second level an AND gate whose input are going to be the output or two OR gates. And you can see that here the two levels are, the first level is OR and the second level is AND. So if you find a circuit that is asking for an implementation in two levels or in two levels of OR and gates, indirectly they are telling you that you have to look for the minimal products. Okay? I think this is quite easy to understand. Just note that adding inverters doesn't increase the number of levels, okay? Inverters doesn't affect as logical gate when we count levels, only the other gates, OR, NAND, etc. Well, we continue. in this slide we have a summary of the simplification algorithm. We have here the steps that we have to follow when we are given a function and we have to simplify it. Remember that the target of simplifying a function is to obtain a simplest and a cheapest circuit. So the first step is to draw the appropriate Karnaugh map that is going to depend on the number of variables. Okay, the number of cells is going to depend on the number of variables, being the number of variables this n here. We are going to draw the Karnaugh map depending on the number of variables, but the second step is to represent them in terms. I mean, is to fill the Karnaugh map with the ones in the cells that we have to put the ones. We have seen several ways of doing it. You can start with the truth table, for example, and translate the ones in the truth table into the Karnaugh map, or you can work directly with the function. You need to have the function expressed algebraically in a disjunctive normal form to do this, for example, okay? Because you have to use product terms to find the ones. Once we have the ones inside the cells, we are going to add the don't care condition. Remember that for every combination of the input for which the output is not clear or is not defined, we add an X in the output. The following step, we are going to obtain the prime implicants. Remember, we are going to find the largest possible allowed group of ones to covering all the function. And we can use the don't care conditions to find the largest possible and as few as possible prime implicants. Once you have all the prime implicants, you have to identify how many of them are essential prime implicants. The essential prime implicants, remember, are those covering distinguished cells, so they have to be included always in the function, in the minimal sum. When we include in the minimal sum the essential prime implicants, we are going to check how many ones of the function are covered in the Karnaugh map. If all the ones are covered, we have finished and we have reached the minimal sum, just using the essential prime implicants. If we have certain ones uncovered, we have to explore all the possible combinations using the rest of prime implicants to cover all the ones of the function. And we are going to have like an structure or a tree, as we saw. So we are going to obtain several irredundant sums. When we have all the redundant sums, we are going to check which of them has the fewest, the smallest number of prime implicants. If we have several irredundant sums with the same number of implicants, we are going to look for the one with the number of literals that is the minimum, and that is going to be the strictly minimal sum. This is just doing exercises, practice, and you are going to automatize these steps. So once we know how to minimize a Boolean function, we are ready to design a digital system. Specifically, as I told you, we are going to work with combinational systems. And this is the algorithm that we are going to use. Firstly, you have to understand the problem definition. You are an engineer. You have to understand the problem definition, the input and the output variables. Okay? Once we have the input and the output variables, according to the problem definitions, we are going to build the truth table. With the truth table, we are going to draw the Karnaugh map, and we are going to obtain the minimal expression of the function. And once we have the minimal expression, we are going to build the logic circuit with the logic gate that we know. The best way of doing it is obviously doing exercises. I want to give you an example about this thing of identifying the problem. Why? Because you are engineers, but normally when you are in a company, maybe your customer is not going to be an engineer, so this person is not going to be able to give you the information in technical language. You are going to have the problem definition in natural language, and you have to translate this natural language in technical language that can be applied to digital systems. Imagine, well, we are going to see a quick example. Imagine that we are going to calculate A is a function that are the students that pass the subject. So if it's 0, it's false. So they failed the exam. If 1, they passed the exam. Okay? True and false. Failed and passed the exam. So we are going to build a function with this natural language in which we are going to calculate the student passing the subject. So if the function is, if we have that B is an input, that means that we are the students, for example, that have studied, so they master the subject. So is 0? No, they haven't studied. If 1, yes, they have studied, so they master the subject. And C is going to be, for example, the student that copy from others. So no, they don't copy. Yes, they copy. So we can say, for example, that the function A, that are the students that pass the subject, can be the student that has studied plus the student that has copied. So if this is 1, we have a 1, so they pass the exam. And if this is 1, this is 1, they have copied, so they are going to pass as well. And they both of them can be 1 at the same time. Maybe they have studied and they also copy. So in both cases, if you check to the truth table of the OR gate, we have this case. So the only way of failing the exam is you haven't studied or you don't copy. But we can add another variable. Imagine that P is a student that are surprised copying, because I see you copy, so you fail. So if I see you, you fail. If I don't see you, you passed. So now the function can become B, you have studied, or you copy, and I don't see you. Okay? If I don't see you, it's P negated. So this is just a silly example of how to translate natural language into a Boolean function. Normally, we are not going to build the function in the first step, but in the last step. Normally, we are going to start building the truth table. Okay? So this is just an example. So I hope that you are not you are not going to be influenced by this example. All of you are going to be this. Okay. We continue with an exercise of logic design. The exercise tells the following. Exercise: design a circuit that sums two binary numbers of 2 bits. Okay, this is the natural language specification. The first step, analyze and understand the problem definition, identifying the input and the output variables of our system. We are going to have a sum of two numbers, and these two numbers are 2 bits length, 2 bits long, sorry. So the input variables of our systems are two numbers that have 2 bits. So I can write number A like this and number B, for example, like this, because they have 2 bits each. So at this point you can see that we are going to have 4 inputs, 2 inputs from this number and 2 inputs from this number. Each bit is an input. And now we have to see what the output is. If A, that is equals to this, and B, that is equal to this, is a number of 2 bits, with 2 bits we can have we can have 4 possible combinations. So we can codify numbers from 0 to 3. So A is going to be in the interval from 0 to 3, and B as well. With 2 bits we can count until 3. So the sum of both of them is going to be between 0 and 6, because in the maximum case we have 3 and 3. So we have 7 combinations here. From 0 to 6 we have 7 combinations. How many bits do we need to codify 7 combinations? We need 3 bits, because with 3 bits we can codify until 8 combinations, and with 2 bits until 4. So we need 3 bits. So our output is going to be a number of 3 bits. So now we know that we have 4 inputs and 3 outputs. The following step is to build the truth table. So let me draw the table and we continue. So here we have the truth table. We have 4 inputs, so we have 16 possible combinations in the input, and we have, as we have seen, 3 outputs, because the output can be a number up to 6. So now we have to fill the truth table in the output using the definition, the problem definition, and the output has to be the sum of A plus B. So we do the sum and write here the result for every combination. So in the first row we have 0 plus 0 is 0. I suggest you to draw these lines because it helps you to build the truth table. So 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3. 1 plus 0 is 1, 2 plus 2 is 4, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4. I'm just summing numbers in binary and writing here the result. 2 plus 3 is 5. 3 plus 0 is 0, is 3, sorry. 3 plus 1 is 4. 3 plus 2 is 5. And finally 3 plus 3 is 6. So we have built the truth table just using the problem definition. So with the truth table we can apply already the method of simplifying functions. In this case we have 3 outputs. Every bit of the output is an output because we are working in the digital domain. So in this case we have to build 3 Karnaugh maps of 4 variables, 1 Karnaugh map per output. So let me draw in the Karnaugh map. So here we have the 3 Karnaugh maps. Remember, we have put here the variables, starting always with the most significant variable and continuing with the rest. Okay? Otherwise, you're not going to have the same order in the Karnaugh map cells. We have sorted the rows and columns using gray code order. Okay? Important as well. So we have 3 Karnaugh maps, and normally we are going to specify at the bottom part of the Karnaugh map the output that belongs to that Karnaugh map. So this is going to be the Karnaugh map of output S2, output S1, and output S0. So now we fill the zeros of each output in the Karnaugh map. So we are going to start with output 2. So we have 4 zeros in the first column. Now we have 0, 0, 0, 1, and here 0, 0, 0, 1. So 0, 0, 0, 1. In order to fill, I'm looking the combination form by each row and column. Okay? Remember that. So now here we have 0, 0, 1, 1, 0, 0, 1, 1, and finally we have 0, 1, 1, 1. 0, 1, 1, 1. I insist, check that I am filling in the right place the ones, just checking the combinations in the outputs, in the columns and the rows. So I'm going to fill the second Karnaugh map with S1. So I'm now here in this column of the output. I have 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, and finally 1, 0, 0, 1. 1, 0, 0, 1. And finally the last output is 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, and again 1, 0, 1, 0, 1, 0, 1, 0. And now we are going to apply the algorithm of the minimization, of the function minimization, to obtain the minimal sum. So I'm going to start with S2. So we are going to look for the prime implicants. Remember, the largest implicant possible, covering all the ones of the function. So here, normally we start with the largest implicant that we see. It's clear that we have this one. And we still have to cover the others 2 ones. So I'm going to put this one here. This one here. So these are the 3 prime implicants that we can find in this function to cover all the ones. We don't have more prime implicants. So we are going to translate them into product terms. So if, for example, this is implicant 1, this is implicant 2, and this is implicant 3, we have that implicant 1 is, remember, we look at the variable that don't change. The one doesn't changing, that are not changing, is A1, that is non-negated because it's 1, and in the rows is B1, that is non-negated because it's 1. So in the implicant 2, we have that in that column we have a column, so both variables here are not changing, and both of them are 1, so they are going to appear non-negated, not complemented. If we look at the rows, we have that is B0, the one that is not changing, and is not complemented because it's also 1. And finally we have implicant 3. In implicant 3 we have a row, so both of them are not changing, both of them are 1, so we are going to have both variables non-negated, and if we look at the columns, we have that the one that doesn't change is A0, non-negated because it's a 1. So we have the 3 prime implicants already defined, because I insist this is an allowed group of 1, but these are the implicants. Okay, so now we are going to look for the essential prime implicants, that are those covering distinguished cells. In this kind of math, it's quite easy to find the distinguished cells. Remember, the distinguished cells are those that are only covered by 1 prime implicant. This is a distinguished cell because it's only covered by implicant 3. This one is another essential cell, distinguished cell, sorry. And these ones are as well distinguished cells because they are covered only by implicant 1. So the 3 of them are essential prime implicants because the 3 of them are covering distinguished cells. So all of them are essential prime implicants. So I have to start the minimal sum including the essential prime implicants. That are all of them. And obviously when we include all the essential prime implicants, we are covering all the ones of the function. So we have finished. The minimal sum for this output is this. So S2 is this output. So we have finished with the output 2. Now we are going to solve the second Karnaugh map. This is more complicated because we have distributions of the ones that is more complex. So we have to identify all the prime implicants. Again, here we have 2 prime implicants because we cannot group these ones with more ones. So even if it's a really small prime implicant, it's a prime implicant. So we have as well this one, and this one. Okay, and in the upper right corner we have this one and this one. So we have covered all the function of the ones of the function with prime implicants. We don't have more prime implicant. So now we are going to translate them into product terms. So for example, this is going to be implicant 1. Implicant 2 is going to be, for example, this. Implicant 3 can be this. You can use a different assignment you want. This can be implicant 4. implicand 5 and implicand 6, and we translate this into product terms. So implicand 1 is going to be these columns that are A1 and A0, both of them negated because their value is 0. And here we have, in the rows, we have that the variable that doesn't change is B1, not negated because its value is 1. Implicand 2 is going to be the value of this column, that is A1, A0, and A0 is negated because it's 0. And if we look at the rows, we have that the variable that doesn't change is B1 negated because it's a 0 in both cases. Implicand 3, we are going to have the values of this row, B1 and B0, both of them negated because their value is 0. We are here just here in the columns, the variable that doesn't change is A1, and it's not negated because its value is 1. Implicand 4 is this one, so we have the value of the row, that is B1, B0, B0 negated because it's 0, B1 not negated because it's 1, and if we look at the columns, we have that the variable that doesn't change is A1, and in this case is negated because it's 0, 0 and 0. Implicand 5 is this one that is really small. We have to include all the variables. In fact, it's a min term because all the variables of the function appear. So A1, A0, B1, B0. A1 is A1 is negated because it's a 0. B1 is negated because it's a 0, and the others are not negated. And finally, implicand 6 is another min term because we have all the variables of the function in it. Is A1, A0 not negated, and B1 and B0 not negated. The values of all of them is 1. So we have this. The second step, again, we are going to identify the distinguished shells. This is a distinguished shell, this is a distinguished shell, a distinguished shell, a distinguished shell, a distinguished shell, and a distinguished shell. So all of them, all the prime implicants are covering a distinguished shell. So everyone is a essential prime implicants. So they are going to be in the minimal sum compulsorily. Okay, so I'm not going to write the value of the variables because it would be quite long. So we can check it, but it's not necessary. If we include if all the prime implicants are essential prime implicants, we know that we are covering all the functions, including them in the minimal sum. And finally, we solve the last map. In this case, we can group the ones like this. Remember that we can wrap the Karnaugh map horizontally and vertically. So this can be implicand 1, and this can be implicand 2. We translate them into product term. Implicand 1 is A0 non-negated, B0 negated, and implicand 2 is A0 negated multiplied by B0 not negated. Remember, we are looking for the variables that remain constant across all the implicants. Okay, so again, all of them are prime implicants because all of them are covering distinguished shell. Distinguished shell, distinguished shell. Remember that a distinguished shell is a cell that is covered only by one prime implicant. So, since they are all of them essential prime implicants, we have to include them in the minimal sum. And we know that with them we are covering all the ones of the function. So the function is covered. With implicant 1 we are covering these ones, and with implicant 2 we are covering these ones. So we have covered all the ones of the function. So we have finished the minimization of the function. The last step is to obtain the logic diagram of the function. Okay, using a two-level AND OR OR, or we can use as well NAND gates and NOR gate, and we are going to see this later. For the moment, we are going to work with two levels of AND OR 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 AND. So, well, since we have obtained the minimal sum, we are going to have a AND OR two-level implementation. You have to translate every expression in a logic circuit, so the output is going to be formed by 3 logic circuits. Since I don't have space here, I'm just going to draw this logic circuit that is the smallest ones. So the output 0 of your system is going to be a sum whose input are two AND gates that are formed by A0, B0, A0 negated, and B0. Well, this is a mistake, sorry. B0 is negated as well. So this is A0, B0 negated, and this is going to be A0 negated multiplied by B0. So we have finished the logic design of the system for the output at 0. We have to build also this circuit, okay? The other circuit of the output 1 and the output 2. The circuit are going to be larger than this, but in the end we are going to have 2 levels of gates, AND OR. If you can choose the logic gate that you want, you can see that this is in fact an XOR gate. So the output should be much easier, sorry. Why? Because if you remember the XOR gate, you have to learn the truth table of the gate, okay? The truth table of the XOR is like this. When the input are different, the output is 1, and when the input are the same, the output is 0. So now we can build this using the minterms in which the function is 1, just applying the Shannon expansion theorem. Remember, we have 2 variables and we are going to include the minterms for which the function is 1, that is the minterm 1 and the minterm 2, that is equal to AB here, minterm 1 and minterm 2, in minterm 1 A negated, B not negated, plus minterm 2, that is A non-negated and B negated. And this is the same as we have here. So it's an XOR. Okay? So if you see this expression, this is the XOR gate. So this is our first example of the design of a logic circuit. Just starting with a natural language specification. We have built, we have detected, we have identified the inputs, the outputs, and once we have the input and output, we have built the truth table here, and we have filled the truth table for the output using the specification given by the problem. Okay? So we are going to proceed always following this reasoning for all the possible problems that we are going to find when designing combinational circuits. Now I'm going to explain, if I find the cursor, I'm going to explain this, why we can build a logic diagram of any function using NAND and NOR gates. We are going to see the concept of complete set of operators. I'm going to move this, sorry. So what's a complete set of operators? Complete set of operators. So if you remember the Shannon expansion theorem, it says that we can express any function as a sum of minterms where the function is 1, or as a product of max term where the function is 0. We saw this in topic 4. This is quite important, this consequence. So what is this? A sum of minterms is a sum of product term, because a minterm is a product term, and a product term is a product. And this is a product of max term. A max term is a sum term, so finally it's a sum. So we can express any function that we have in terms of sum of products, as well the negation. We are going to consider the negation always included of a product of sum. So that's why we can finally also build a logic circuit using a two-level OR and OR. Okay? Because this means that we have a complete set of operators just using the logic sum, the logic product, and the negation. This is a complete set of operators. Why? Because just using these three operations, we can express any possible function. This is true. We have seen that we can express any function in a disjunctive normal form or a conjunctive normal form just using this operation. So now we are going to see this. What happened with the NAND gate? Is the set of the NAND gate a complete set of operators? So to check it, we have to demonstrate that using NAND gate we can implement the logic sum, the logic product, and the negation. So we are going to check it. So the negation using NAND gate. This is an inverter, this is the negation. We can do this with NAND gates. Yes. If we have a NAND gate here and we connect the same input to both, the same variable to both inputs, we're going to have this. Remember that the NAND gate is just the complementation of the AND gate. This. And if we apply here the theorem 3, the idempotent law, we have this. And this is the input negated. So connecting the same variable to both inputs, we can implement an inverter using an AND gate. You can check this also using the truth table, okay? And the NAND gate is just the opposite of the AND. So if the variable is connected, if the same variable is connected to both inputs, we are going to have just the opposite when the variable is 0 and when the variable is 1. So the second, can we get an AND gate using only NAND gates? This is quite simple. So we have to reach this. This is the AND, remember. Using NAND gates, we are going to see how. If we connect X and Y to an AND gate, we have here this, okay? If we connect this output to both inputs of another NAND gate, remember that this is like an inverter. We are going to have this. With the theorem 4 of the involution law, we have that negates twice is like non-negate. So this is the logic product. So just using NAND gates, we have reached the AND operation. And finally, the OR operation, the logic sum. We have to reach this expression with NAND gates. So we are going to do the following. If we have this and we negate twice, just applying again the involution law, the theorem 4, this is the same. Now we can apply here the theorem 8, the De Morgan's law. And we are going to break only the first complementation. So we are going to have this. Okay, and this is an inversion of the variable that can be done with an AND gate, and this is a negated product that is an AND gate. So here we have an expression that can be implemented only using NAND gate, so we are going to do it. We have X, we are going to negate X with an AND gate. This is Y, we are going to negate Y, and finally we are going to pass this through another NAND gate. So we are going to have the negated product of the input, and following this reasoning here, we know that this is equal to X plus Y. So since we can perform the inversion, the AND and the OR operations with NAND gates, the NAND gate set is a complete set of operators, and we can build any function possible just using NAND gates interconnected. I'm going to tell you that the NOR gate set, the NOR gate is also a complete set of operators, and we can express any function using NOR gate. I'm going to I'm going to leave for you this demonstration. It's quite similar, and we are going to apply the same theorems and actions that for the NAND gate example. So you want, you can check it. So that's why we have this here. With NAND and with NOR, we can as well build a logic diagram interconnecting logic gates and represent any function. It's perfectly normal that you find an exercise that asks you to implement a given function using just NAND gate or only NOR gate or two level of an OR gate. So you have to master this. I'm going to give you some trick about how to manipulate algebraically functions so that you can build them just with NAND gate or NOR gate. So imagine that we have this function, this three variable function, so this function, the first question is a normalized form of the function? To be a normalized form, this expression has to be a disjunctive normal form or a conjunctive normal form. This is a disjunctive normal form because it's a sum of product terms. Okay? So this is the disjunctive normal form. We can get the conjunctive normal form, I mean a product of sum, just applying the distributive property with set. So we have now this, and in this case this is a product of some terms. Okay, a product of some terms. So this is a conjunctive normal form. So imagine that they tell you that you have to build this circuit, the circuit that implements this function on using only NAND gates. Okay, using only NAND gates. So the best way to do it is to have the disjunctive normal form of the function. If you don't have the disjunctive normal form, you can manipulate algebraically the function to get it. So f is like this. Remember the disjunctive normal form. And how do we obtain an implementation with NAND gates? Quite easy. We are going to negate the function twice. We are going to apply the involution theorem. So if we negate twice the function remains the same. And now we are going to break only this complementation, the first complementation, using the De Morgan's law. And this logic sum is going to become a logic product. So if you check the new expressions, this is the inversion of x that can be done with a NAND gate. This is a logic product negated, and this is a logic product negated. So all of them are NAND gate. So just negating twice and applying the De Morgan's law once, we have passed from the disjunctive normal form to a NAND gate implementation. We can do the same, but using the conjunctive normal form, but you are going to see that it's not the ideal scenario. No, sorry. We are going to see this later. I prefer to do this before because it's easier to understand. So now we are going to use NOR gate. We have seen that the NAND set and the NOR set are complete set of operators. What happens if we want to do this using NOR gates? So we are going to do the following. We are going to negate twice each term. Each term is going to be twice negated, and so it remains the same. So if we apply the De Morgan's law in the first complementation of each term, we are going to have that this logic product becomes logic sums. You can this is x because actually is x negated twice, so it becomes x. So once we have this, we still need this logic sum to be negated, so we are going to negate again the whole expression. If we negate twice the whole expression, it remains the same. And now everything is expressed in terms of NOR gates. Set negated can be obtained with NOR gate, just connecting both inputs to the same variables. This is a negated sum, this is a negated sum, this is a negated sum that is negated again. So we can build this just using NOR gate. This is more complex. Why? Because actually the best method to implement a function with NOR gate is using the conjunctive normal form. We are going to say it. The conjunctive normal form is this. So it's as easy as negate twice the whole expression, just as in the case of the NAND gates and the disjunctive normal form. So if we negate everything twice, we have this. We are going to break the first complementation using the De Morgan's law, so this logic product is going to become a logic sum. So this can be done with an OR gate. This can be done with an OR gate. It's just a complementation. This is a negate sum that is an OR gate, and this is a negate sum that is an OR gate. Everything has been implemented easily with NOR gates. So just a summary. If we have to implement a function with NAND gates, we are going to start with the disjunctive normal form of the function, and we negate all twice. And you know, we apply the De Morgan's law only to one complementation. And to implement everything with NOR gates, we are going to start with the conjunctive normal form, and we are going to negate all twice. We apply the De Morgan's law to the first complementation, and we can implement functions just using NAND and NOR gates. You can see that algebraic manipulation, the Boolean algebra theorems or actions are really useful when working with digital circuits. So, well, we are going to see more things. There is only one thing remaining in the topic, that is the analysis of logic circuits. We have seen the design algorithm, the design of logic circuits. You know, we translate from natural language into digital language, we identify input and output, we build the truth table according to the problem definitions. Once we have the truth table, we are going to build the kind of map of each output. We are going to simplify the output using the tool that we have seen. And when we have the minimal expression, we build the logic diagram interconnecting logic gates using AND OR levels or NAND or NOR gates. We are going to apply this in every exercise that we are going to do about the design of combinational circuits. The other thing is the analysis of combinational circuits. We are going to find exercise like this, in which we are going to have a logic circuit, and we have to calculate the output of the logic circuit. For example, this logic circuit has 3 outputs, as you can see. We have finished the circuit, the analysis of the circuit, when we have every output expressed in terms of the input of the circuit. So this is the algorithm that we are going to follow. I think that the best way to see this is with an example. If we have this logic circuit, we have to identify the input of the circuit. The input are here. Okay? So, for example, the input can be X, Y, Z, and W. And the output can be Z1, Z2, and Z3. We are going to identify the levels, how many levels the circuit have. So remember, we are going to define a level every time that we connect one gate after the other. So here in this circuit, we have 3 levels. The input levels, the input that is going to is going to be the first one, the output that is the third level, and a second level that is an intermediate level. Here we are going to have intermediate variables. Okay? So we are going to calculate the intermediate variables, and little by little we are going to have the value of the inputs here in expressions. For example, A1, A2, etc. So finally we are going to have the output calculated in an algebraic way in terms of the input. We are going to see an example. Here we have 4 variables that has been called A, B, C, D. We have 3 outputs. We have 3 levels, as you have seen. And we are going to define the intermediate variables. Okay, the intermediate variables are the outputs of the levels that are not the output of the circuit. The intermediate variable here are P and Q, is R. So we calculate the intermediate variable. In this case, P is the output of an OR gate, so is A plus B, and Q is just negated D. Level 1, level 2, level 3. So this is the output of level 1. The output of level 1 are going to be the input of level 2. Here we are going to have an output that is in fact Z1. This output is going to be P and with C, okay, because here we have C, and this is going to be A plus B multiplied by C, logic product. Okay, R is going to be the XOR of P and C, because here we have P and here we have C. Okay, So we have the value of set1, the value of, sorry, this is not XOR but an OR gate. R is an NOR gate, so is P plus C negated. We already have the value of P, so we can substitute P here. So set2 is the XOR of P plus C negated and R. Okay, and R is this value. I mean, if you go step by step, finally you are going to have all the outputs in terms of A, B, C, D, just substituting the value of P, Q, and R that are the intermediate variables. I think that this is quite easy to understand. The only thing that can be more complex about this is that when you have the value of all the outputs, you can have complex expressions. So you need certain domain of algebraic manipulations to convert this expression in a normalized expression. For example, the disjunctive normal form or the conjunctive normal form, etc. In fact, we can practice, for example, obtaining the disjunctive normal form of set 2 that is quite complex. So we can go here and just practice. So according to the exercise, we have obtained that set 2 is this A plus B multiplied by C XOR with A plus B plus C negated. So imagine that we have to obtain the disjunctive normal form of this. Remember, the disjunctive normal form is a sum of product terms. Okay? So we can go little by little. If we apply here the distributive property, we have this A C plus B C that is XOR with A plus B plus C negated. So we are going to see the XOR operation. Remember, I told you that the XOR operation is a sum of the first literal multiplied by the second negated, the first literal negated multiplied by the second non-negated. This is the XOR if you look at the midterm of its truth table. So we are going to apply this little by little. So this term non-negated multiplied by the other term negated plus the first term negated multiplied by the second term non-negated. Just in the same way, remember, it's just applying the XOR. So now we apply the properties of the Boolean algebra to this expression. We are going to have the following. We can remove this using the involution theorem, because negating twice is like non-negating, and we can apply here the distributive property in this product. So we are going to have the following. You can check it, okay? I'm going to do it. A C plus ABC plus ACC plus ABC plus BBC plus BBC plus this expression. Note that I have applied the distributive property here, but I have this product untouched, because otherwise it's going to be difficult to operate with. So now we can look for simplification that we can do here. For example, we have terms that appear twice, and you know that x plus x is x from the theorem and axiom of the Boolean algebra. So, for example, we can remove this term because we already have it here, and this term, okay, because we already have it here, and this term because it's here repeated. So we can simplify. And now we know this is the idempotent law, the theorem 3. We know as well the dual expression of the idempotent law is this. So if we have a term that is a literal that is repeated in a product, we can remove the literal as well. So here we can get rid of this A and this B because they are repeated. Okay? So we have AC plus ABC plus BC plus the other term that I haven't touched yet. So we continue with the simplification. Now we can see that AC is here again, okay? Or we can see that BC is here. So using either this or either these two terms, we can use the absorption law, the absorption theorem. That is the following. Okay? So we can get rid of this term. Okay? You can see it. AC plus ABC. We have here AC and we have here AC. So we have the same multiplying something. We can apply the same theorem if we want using these two. Okay? So we have finally this. We have simplified a lot of terms using the axiom and theorem. Once you practice, this is quite fast. I'm going slowly so you can see it. And now we are going to process the other term, just applying the De Morgan's law. Well, I have realized that I made a mistake when copying this. Sorry. This was like this. So this is going to be like this. If we apply again the De Morgan's theorem, we have the following. So again, we can apply the distributive property. And we are going to have the following. You can check it if you want. So now we are going to see if we can remove some of the terms. We can remove this because it appeared twice using the idempotent law. Once we have this, we can absorb these terms because C negated appeared here, so we can remove this term with the absorption law. And now I think it's all. We can absorb this term as well because we have here C negated. So we have AC plus BC. I told you that the absorption law is really powerful. Now we have here A negated, B negated plus C negated multiplied by ABC negated. We continue. We are going to have the following. You can check it using the distributive property. So the idempotent law, we can remove the terms that are repeated. A B negated is repeated here. C negated is repeated here. And in fact, this is the same. A negated, B negated, C negated, A negated, B negated, and C negated. So we have again the idempotent law here. So we can remove one term completely. So in the end, we have AC plus BC plus ABC negated, and this is a sum of product terms, so this is a disjunctive normal form. Well, the starting expression was complex, so we have done a lot of calculations, but you can see that we can reach the disjunctive normal form always just manipulating algebraically a function. With this, we can build an OR implementation with logic gates or an AND implementation negating twice. Remember what we have just seen. We are going to do now another exercise of logic design because I think that they are more complex than the logic analysis. In the end, it's just when you are analyzing a logic gate circuit, it's just going step by step and not making mistake when building the algebraic expressions. But well, logic design is more interesting, I think. So, for example, exercise. The tablet is also tired. Exercise. The exercise tells the following. Designed a system that detects if a BCD digit is a multiple of 3. So this is the only specification that we have. We have to design a system that detects this. So the first step, remember the algorithm of the logic design. Identify, no, this is the analysis. Analyze and understand the problem definition. Identify the inputs and the output variables. So, what are the inputs and the output variables? We are going to think. What is a BCD digit? It's a decimal digit, is 1 decimal digit. So, a digit that goes from 0 to 9, that is going to be expressed using 4 bits in binary. So, we are going to have 4 bits. 1, 2, 3, 4. Well, just a comment about the previous, before I forget it. So, when I'm solving this, because I've just remembered, you may see that when I calculate the products, and we have, for example, this, that here we have ABC, I always sort the terms. For example, if I have ABC, I don't write BAC or CBA. I always follow this order from the most significant variable, because if I always follow the same order, it's going to be easier to see when we can apply the properties. So, for example, I know that I have here ABC and I have here ABC because I have followed the same order. If I use here, instead of ABC, BCA, it's going to be more difficult to identify the properties. So my advice is that when you write the result of the intermediate operations, you always sort the literals starting with the most significant variables and following with the rest. So after this interruption, we follow with the exercise of logic design. So my input is going to be 4 bits. Why? Because it's a BCD codification, and you know that the BCD codification works this way. So there is no excuse. You have to understand and to memorize and to learn codifications. So my system has 4 inputs. What is going to be the output? The output is going to be the detection of a multiple of 3. So I can say that the output is, for example, 0. It is not a multiple of 3. It's going to be a 1 if it's a multiple of 3. Okay? So we have to translate from this sentence to inputs and outputs. The input is clear because it's a BCD digit. So we have 4 bits to codify the BCD digits. And the output, we have only 1 bit because the answer is yes or no. Is a multiple? Yes. Is a multiple? No. So we only need a bit. So once we have the number of inputs and output, and we have assigned literals, numbers to the variables, the next step is, as you know, build the truth table. So just give me 1 second to draw the truth table. So here we have the truth table. Remember, we have 4 inputs, so we are going to have 16 possible combinations of the inputs. Now we have to fill the column of the output following the problem specification. So we have to detect multiples of 3. So we are going to go through every number and we are going to check if it's a multiple of 3. The first combination is 0. Well, we can consider the 0 as multiple of 3. Maybe those of you from the double degree in mathematics things different. Let me know. We are going to consider that the 0 is a multiple of 3. So the 0 is a multiple of 3. The number 1 is a multiple of 3. No. The number 2. No. The number 3. Yes, 3 is a multiple of 3. In fact, the multiple of 3 are going to be 3, 6, and 9. And the others are not multiple of 3. It's basic mathematics. Okay? So we have 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. We may follow, for example, is 10 a multiple of 3? No. But this is a mistake. Why I don't have to follow with the rest of the combinations? Because of the following reason. We have a BCD digit. So I know that it's going to be a value from 0 to 9. So we have 0 here, we have 9 here, and the rest of the combination from 10 to 15 are not going to happen. Sorry, because it's a BCD digit. So what happens with the rest of combination? They are not going to be in the input ever. So we don't care about the value of the output for them. So here we have don't care conditions. Okay? So this is our truth table. We have one output, so we are going to build one Karnaugh map. So the Karnaugh map is this. Well, just give me 1 minute and I draw the Karnaugh map. So we have here the Karnaugh map. I'm going to fill the Karnaugh map using the values of the truth table. We have here in the first column 1, 0, 0, 1. So 1, 0, 0, 1. The second column we have 0, 0, 1, 0. 0, 0, 1, 0. In the other column, this one, we have 0, 1, x, x. 0, 1, x, x. The order that I'm following when filling the table is related to the gray code, because we can see that here we have 0, 1, 2, and 3. So this is the reason why I'm jumping this way when filling the Karnaugh map. And this column here is all of the cells equals to x. So now we apply the algorithm of the minimization of a Karnaugh map. So, as you know, first step, find the prime implicant. So we find the prime implicant. We are going to use, for example, this color. So we have to cover the ones. In order to cover this one, I'm going to use the X to form a large prime implicant. This one here cannot be grouped with another one. And what happens with this one? We can use the X in the other side to form a 2 elements prime implicants. The bigger the prime implicants, the better. So for example, we can use this X. And what happens with the other one? We can use the X to have a bigger prime implicant. So these are the larger prime implicants that we can form using the X. So now we are going to assign names, as you know, to this allowed group of 1. This is implicant 1. Sorry, because the tablet is quite slow, for me it's difficult from time to time. Implicant 1, for example, implicant 2, implicant 3, why not? And implicant 4. So we are going to translate the allowed group of 1s in product terms. Implicant 1. The variable that doesn't change in the columns is A3, that is not negated because it's 1. And in the rows, A2 that is not negated because it's 1. Implicant 2. Implicant 2 is this one. The variable that doesn't change in the columns is A2, and in the rows, both of them. A1 and A0 negated because A0 is 0. And finally, not finally, because we have another one. Implicant 3 is the variable that don't change is A2 negated. In this row, A1 and A0, both of them not negated because they are 1. Implicant 4. Implicant 4 is just this element. So it's just one element. It's a min term of the function. We have all the variables implied. So all of them are 0. The next step, we are going to identify the essential prime implicant using the distinguished shells. We have here a distinguished shell. We have here a distinguished shell. Here we have a distinguished shell. Here, all of them contain distinguished shells. So all of them are essential prime implicants. So we know that in order to obtain the minimal sum, we have to include all the essential prime implicants. So implicant 1 plus implicant 2 plus implicant 3 plus implicant 4. We know that we are covering all the function with implicant 1 these ones, with implicant 2 these ones, with implicant 3 these ones, and with implicant 4 these ones. Since all of them are essential prime implicants, we only have an irrandom sum, that is the minimal sum. So, have we finished? No, because we have to build the logic circuit. So we are going to build the logic circuit. Since we have the minimal sum, we are going to have a two-level of OR gate. So A0, A1, A2, and A3. So the first implicant is going to be the AND, the logic product of A3 and A2. So we have here implicant 1. The implicant 2 is an AND gate of 3 inputs. One input is A2, the other is A1. Sorry, because of the behavior of the tablet. And the other is A0 negated. The other implicant is implicant 3. that is going to be A2 negated, A1, I'm going to take it from here, and A0 not negated, so we can take it from here. And finally we have implicant 4, that is an AND gate of 4 inputs and is A3 negated, A2 negated, that I'm going to take from here, for example, A1 negated. A1 negated is here we have A1, and finally A0 negated. I'm not sure if I have made some mistake, just checking it. You can think of a better way of doing it, okay? I mean, this is a quite mess because I didn't spend a lot of time thinking about how to wire this, and all of them are going to be the input of a OR gate. So this is the implementation with a logic circuit of the problem. So we have finished the problem in this step. Maybe we can check, we want to check what happens with the zeros. Here we have chosen the ones, but what if we use the zeros? We are going to see what happens if we use the zeros. Maybe the circuit is simpler. I don't know. We have to check it. So this is the same Karnaugh map of before, of this, but just keeping the zeros and not drawing the ones. So again, we are going to look this time for the prime implicates. Remember, not implicants, but implicates. So we can use the X if it's interesting for us, remember. For example, this 0 here in the corner can be a group using this X. This one can be grouped like this. We can use to cover the 0 in the right top corner. This 0 we can use, for example, of this X to have a really large prime implicant. The larger the prime implicant, the smaller the product term that is associated. Remember, we are interested in the largest possible. So we can as well use, for example, to cover this 0, we can use, sorry because I undo twice. To cover the 0 as before, we can do this using the X. And to cover the remaining 0, we can again use a 4-cell group. So now we have found the largest possible prime implicates using the X. So we are going to assign names and to solve the Karnaugh map. I like to use imp from implicates to distinguish between implicant and implicate. And now we solve the circuit. 1, 2, 3, 4, 5. So now we assigned some terms to those allowed group of zeros. Implicate 1. The variables involved are a2 plus a1, the variables that don't change across the group. So a2 is 1, so it's negated. And a1 is 0, so it's not negated. Remember, it's just the opposite as in the case of the implicants and the product terms. Implicate 2. Implicate 2 involves a3 plus a0. You can see a3 and a0 because they are the variables that don't change. a3 is 1, so it has to be negated, and a0 is 0, so it's not negated. I have made a mistake. This is implicant 3. Implicate 3. Implicate 2. Implicate 2 is this one. So the variable that doesn't change is a2 plus a0. a2 is 1, so it's negated, and a0 is 1, so it's negated. Implicate 4. Implicate 4 is a3 plus a1 plus a0. A3 is 0, so it's not negated. A1 is 0, so it's not negated, and a0 is 1, so it's negated. And finally, we have implicate 5. Implicate 5, we have a2 plus a1 plus a0. a2 is not negated because it's 0. a1 is 1, so it's negated, and a0 is 0, so it appears non negated. So we have all the sum terms linked to those allowed group of zeros. So we have to detect the essential prime implicates. So essential prime implicate, we look for distinguished cells. We have here 1, we have here 1, we have here 1, we have here 1, we have here 1. So I have a distinguished cell in every prime implicate. So all of them are essential prime implicate. The minimal product is going to be that formed by the product of all of them. So this is the minimal product. You can compare with the minimal sum and look for the minimal expression. And here we have 5 sum terms, but here we have 4 product terms. So this is a better implementation because we use a smaller circuit. Okay? So imagine that you have to implement the circuit using NAND gate. What we are going to have to do is use the minimal sum here and negate twice. So the minimal sum and negate twice. And we apply the De Morgan's theorem once. and you can check that negate each implicant is like having an AND operation. It's like negate these expressions. You have an AND operation. So we have the output expressed as connections of NAND gates. Okay? So at this point, I think that we have seen a lot of things. So we can finish the lesson on topic 5. Just study the content, study how to design and how to analyze a logic circuit, and try to do the exercises of the list that I have uploaded in the topic 5 tab in the virtual campus. Okay? I'm going to record another video giving some advices to use a software that is called DITS. DITS is going to be the equivalent of LT-SPICE, but for digital systems. So you can check if your solutions are okay just building your logic circuits in DITS. So I'm going to finish this video, and I'm going to record another really short video about an introduction of DITS. Okay? So thank you for watching. Bye.